Now we move on to the other services which transport layer provides. As we know, error detection is the first step in combating the error and ensuring reliability. At the transport layer, checksum is incorporated, which is used both in the transport layer TCP and UDP. Therefore, we are going to look at it from the strength point of view. In this module, we shall quickly go through how checksum is computed and how can we determine if it is appropriately strong to sustain our transport layer services requirement. The transport layer incorporates error detection. The error detection is implemented in software because it is known that as we go up the layers, it tends to be more software oriented. So checksum is a software implementation of the error detection. Checksum is also termed as checking the sum. What we do is we compute the sum of the octets of the input data and determine a checked sum, and we append that checked sum with the data and send it over to the other side. When the other side receives it, it performs the computations in exactly the same way and uses that checked sum in addition. If it turns out that all the summations are correct, so the data is rated as correct and healthy. And if it is not, an error message is generated. Jonathan Stone wrote a paper titled Performance of Checksums and CRCs over Real Data, and there's URL also that identifies a SWOT analysis of checksum. Here you can see that there is 32-bit data which is divided into chunks of 16-bit each, and then using 1's complement, using 2's complement, addition is performed. In this addition, if there is a carry, it is wrapped around and it is added to the least significant bit, and this addition process continues till it is completed on the leftmost side. So what we get is, we get the sum. Now if we invert the sum, we get the checksum. Now we have 32-bit of user data with 16-bit of checksum. So with this 48-bit of data with the checksum, we send it over to the other side. The other side performs the same process again, and this time the addition on the receiving side is going to be the 16-bit data and 32-bit data and the 16-bit header as the checksum. So 48-bit is added in 16-bit chunks, and when the result is computed, it has to turn out to be all zeros. If it does not, it means there must have been an error midway. The overhead and the computational cost of performing checksum can be looked at in a systematic way. Let's assume that we have m-bit data, and if we were to divide it in n-bit chunks, so the total number of chunks are naturally going to be m divided by n. If the checksum is also computed as n-bit, so the total data that we'll have is m plus n bits. The total data is going to be m plus m divided by n bits. After that, we'll see what is the total number of summation processes which are carried out here. So we see that if we have m divided by n as the total number of chunks, so the total sums we'll have would be m divided by n plus 1. The last plus 1 has been included because we also are adding the sum with the checksum. So is checksum the slam dunk winner? If we were to assume that, we might go wrong because there are few errors which go undetected even with checksum. For example, if we look at these words as 1, 2, 3, and 4, if these are reordered as 3, 4, 1, 2, since we are just computing the checksum as a modular mechanism regardless of the order, it would go undetected. Similarly, if zeros are added to the original data, it would still go undetected. If there were zeros in the original data and somehow these zeros disappear, this again would go undetected. And if a string of 16 zeros is replaced with ones, or a string of 16 ones is replaced with 16 zeros, it is also going to get undetected. Likewise, the multiple errors with sum to 0, for example, 1, 2, 3, 4, if it changes to 1, 3, 3, 3, it would also result into a summing result, which would be all zeros. So these errors go undetected, making checksum vulnerable to certain kind of errors. And we must keep that in mind when designing and modeling any checksum algorithm.